6, it's problem 8, it's one of the ones we did for homework. So the problem is there is a square paper 3 feet long. So it's a square, so that's the length and the width. An open box, which is made by folding up the sides, is to be cut from it by cutting the squares out, one from each corner. So if you cut the 4 squares out, that leaves you with a 5 square, just 1 square in the middle, and, well, 5 faced, sorry, they could be rectangles, 1 in the middle and 1 around. And so this is a diagram of the problem, and the problem asks you to maximize the volume of the open-topped square box. Sorry. So we know that if we name this part here y, and we name these parts that have the dashes on them that are equal x, because the squares are being cut out, which means these have to be squares and they all have to be equal, one from each corner, like that. And then we call the part in between y, and we know that this length here, so this one and this one, both have to be y, because we know that because if there's an x here and an x here, and there's an x here and an x here, then these both have to be the same because the side lengths, the total side lengths, are the same. So the length of y is given as y equals 3. So 3 is from up here, the 3 feet long. So y equals 3 minus 2x because of the 2 x's that are being taken out of it on both sides. So we know the volume of the box equals y squared x. We know that because this is y and this is y. So that's the area of the base. And then we know the height here, and that's the same all along here. We know that is x. So we know from up here we have an equation for y. So the volume equals x and then 3 minus 2x squared. And that equals 4x cubed minus 12x squared plus 9x. And we don't want to simplify it any further because we would like to take the velocity straight from there. So the velocity, sorry, not the velocity, the derivative. So the derivative equals 12x squared minus 24x plus 9, just using the simple derivative rules. And we can factor out a 3 from here. So that's 3, 4x squared minus 8x plus 3. And then if we times the 3 and the 4, that gives 12. And we know what times is to give 12 and adds to give negative 8 is negative 2 and negative 6. And then we put those in, which I skipped that step, but we put those in and we factor out the 2 from each. And that gives you 3, 2x minus 1, 2x minus 3, where x is greater than 0 because it's a length, so it has to be positive. So then we need to find the critical values. So when v prime equals 0, x equals a half, or 3 on 2, and that's just from here because a half times 2 is 1, 1 minus 1 is 0, and then 3 halves times 2 is 3, and 3 minus 3 is 0, and we want to find a 0 for some value in here. And v prime is undefined, never. And v prime, the number line of v prime here, if we put in a number that is less than a half, we get a positive. In between a half and 3 halves is a negative, and greater than 3 halves is positive again. So a max is when it goes from a positive to a negative, and the only place where that is at a half. So there's a max at x equals a half, and when x equals a half, the volume equals 2. And we just got that by subbing right back into the original volume equation up here. And therefore the largest volume possible is at v equals 2 feet cubed. And we need to make sure we put in the units, and we know that from up here. And that's it.